trying to talk about place value, and it's getting all the way digital. And here's how it works. You guys get like, in our system, it's a decimal system, so we're going to use tens. Others, computers are binary, so they use twos. The color part of computers is hexadecimal, so it's 16s. The sexagesimal, which we talked about, is 60s. 60s. So we'll start with decimal because that's what we're used to, mostly. And that is that you get your first column when you first start counting, and that's sort of your ones place, 79. And then it rolls over to your next one, and that's your tens. And then you get your next one, your hundreds, and your next one, your thousands, and so forth. Binary is the same. You get your first column, which is your ones, or we call this the units. It's just a standard way of doing it. And then the next one is going to be your twos. Your binary, and it's going in twos. And then it's going to go in 4 terms of power, so then your 4s, and then your 8s, and then your 16s, and so forth. Decimal, so here's 20, that would be your 1s, and then your 20s, and then your 400s, and so forth. Sexagesimal, there's 60, and then you get your units, your 60s, 1 example, 600s. And 2 place values you got opposed to it will be counting change or change. I could just hand you a whole bunch of change. It would be like me handing you a bunch of change and go, here's a bunch of change. Even though it's quarantine, there's not much like change out there, but it used to be like you can hand a bunch of change. And how much is in here? And you gotta sit there and count through all the pennies and the dirty. It's just a pain to know how much it is. And then otherwise, if I hand you a change drawer and say, hey, and everything's organized, and hey, how much is this? And you go, oh, no problem. You count out like the pennies and the dimes, and each time you can count them up, add them up, multiply them by the number, and put it all together. That's like how to place value, and way better. Cool.
So, real quick, we're gonna go over some number-based systems, most particularly the Babylonians and the sexagesimal system. The Babylonians were modern-day Iraq, Tigris Euphrates, King Cyrus, all the way to Nebuchadnezzar. Some good history to learn there. And an interesting facet about their awesome mathematics is they were base 60, like I said. And the base system, we're base 10 because of this. It's sort of it's a commonality, and that's been around and agreed upon. There's no other real reason why. The Mayans, they were begesimal, that's base 20. And that's most likely because of fingers and toes. And the Babylonians, they were base 60, which is way cool. And it turns out for lots of reasons. And one of them is the way that they think you could count on your hands is, or maybe here I can look at it. So like, I got like 1, 2, 3. And then before I'd have like 3, 6, 9, 12. And on the other hand, I can count some of those 12s off, like 12, 24, 36, 48, 60. And just my 2 hands, I was able to count off to 60. And with some basic memory, we could do 60/60s, and now we're up to 3600s, which is way cool. And another facet of 60 that made doing business, because that's why they were focused on doing math, that was their MO for sure, was tied to this kind of number of other things. And the fact that 60 can be broken down, so let's say we're gonna break it apart by 15 and 4, and we're gonna keep finding numbers that go into those as we go. Right. And so we got these numbers down here. And this is the prime factorization. So if we have 2 2s, a 3, and a 5, we'll get 60. If we have 60, we'll get 2 2s, a 3, and a 5. It's a combination of numbers such that the order doesn't matter. It doesn't matter in which direction we go or however we get to those 2 2s, 3, and a 5. It's just the fact that we have those. And this fundamental theorem, which is created, sort of attributed mostly to Gauss, Euclid has it, just wasn't formalized enough, I guess. And he probably picked up enough on it from beforehand. Simply stated that every number, like whole type number, has its own unique prime factorization. And if you have a prime factorization, it's tied to that. It's like a key. So like, let's say I have like 45, right? And break that apart, 9 and 5, and 3 and 3. Well, if I have 2 3s and a 5, I'm gonna get 45. Or if I have 45, I'm gonna get 2 3s and a 5. And now we've broken it down to the parts that can't be broken down anymore. And that's also ways we can rearrange it in all the different ways we might want to. 60 is kind of special in that regard. So 60, you know, we got like 2 times 30, 3 times 20, 4 times 15, 5 times 12, 6 times 10. Sorry, my numbers are getting kind of small. And that's a lot of different ways that we can parse it down and break it apart, which is really useful. And for the Babylonians and their ways about going about mathematics, that was perfectly well enough. They could figure out the numbers they wanted to figure out. For instance, if you have like the square of area of 2 square feet, or whatever unit that they use at that time, rods, or I don't know what they use. Before that, though, I do have a question that you need to we should figure out, and this is would be the assignment regarding the factors. So consider the natural numbers, 1 to 100. Those are like the numbers that you count with as we first start. The whole numbers have the 0. Which element of this set has the greatest number of factors? You know how like 60 has a whole bunch of them? Well, which one, 100, between 1 and 100? So we're going to quick move into the next question real quick because it'll make things make more sense. We have the previous one, right? And now we're going to have to construct a square with 2 square units, something new. Not really going to talk much more about how you're going to go about doing that. That's just on you. We're going to look at some stuff, and all the information should actually be there then. Ah, cool. And having an area of 2 square units is an interesting concept. So we got 2, maybe we might do inches squared, right? So like it's going to some amount on each direction. And well, we want to know how long these sides are. And if you think about it, like if it's number squared, right? Some number times some number equals 2 inches squared, right? This number times itself has to be 2, right? Well, 1 times 1 is 1. And 2 times 2 is 4. So it has to be between 1 and 2. So maybe like 3 over 2. 3 over 2 times 3 over 2. That's 9 over 4. And in case you need to review, if you want to turn that into a mixed number, so 4 goes into 9 2 times, and you got 1 left over, right? So 1 over 4. So a little bit over 2, we're getting closer. So 3 over 2 is closer than 2 was, right? But we could keep doing that, and we could keep doing that forever, and we would never find a conclusion to it because the fact of the matter is irrational. Which is kind of, to some people, not that big of a deal. To 2, and remember we just did the fundamental theorem of arithmetic, and one thing about that is we can use it to identify square roots real well. So like let's say you have a number like 16, you can break it down, and 4 2's, right? Well, whenever you have a pair of things, you're going to do a square root. So like the square of 16 would be that broken all the way down, and whenever you have a pair, here we end up with 2 pairs, right? So all those come out, so we come out with like a 2 times 2, which is 4, right? Which we know that square root of 16 is 4. Or the square root of 64, but that would be a bunch of 2's and stuff. Now, that same thing holds true too if it's kind of a wonky number like 12, you know? So if you got 12, you're going to break that down. And we get there, right? Now, we already talked about we had a pair, right? So the pair will, as a square root, like 1 times itself, obviously, is no longer a square root. We're done with the symbol. But these numbers that are just hanging out, that are not part of a pair, those stay there. And we're still stuck with this thing, which there's ways around it. But we're times the Greeks, and the fact of the matter is, like the universe has to work in harmony, and all things have to be rational. And for that, it means it's like a rational number is a number that can be written over another number, like 3 over 5 or 7 over 9, or just no wonkiness to it. It has to be able to be written like that. Well, they insisted that it had to be, and everyone was like, no, you can't be. Well, not everyone, but you can't be, because you just can't be. And Hippasus proved it, and they killed him. And later on down the road, Euclid, he proved it again, and I think they listened to him. I don't know. Sort of. You can't get away around it. And so he did a proof of reductio ad absurdum, which means we're going to start out by saying this is true. The square root of 2 is rational. It's written as a ratio of a number over a number. Cool, right? Well, let's do some rearranging. This is more algebraic. Well, the inverse operation of square root and it being and the inverse operation of square root would be to square. So we're going to square both sides. So 2 equals and squared over d squared. And now we're going to take this number that's down here on the bottom, and when there's no like addition and stuff, if it's just division down there, we can just bring it up over here, and it would be multiplying on the other side, right? So it's like inverses. This is more of the algebraic way. You could have some, who knows, way of writing it out. And the algebra is really the Arabic's contribution to mathematics big time. You know, the Indians, so much with the n base 10, that's where we get the Hindu Arabic numerals. So we have all this going in play. It's cool. Well, we can kind of expand this out a little bit more. You know, d squared would be also d times d, and then squared would be n times n, which is kind of useful. Now, if you remember back on the fundamental theorem of arithmetic, like a number can be broken by factors. Like it has so many factors that it can be. And that number of factors can either be even or odd. There we go. That number can be even or odd, and that's the only way it can be. And the thing with that is, well, if you double any number, even or odd, you always end up with an even. Think about it, and you'll find that out. Right. So we're going to double a number here, and if we double it, it's going to be even. And we double a number of factors over here, it's going to be even. But wait, there's one extra one over here, so the even now has 1 plus 1. Even plus 1 is odd. And that cannot be, good friends. And so therefore, this number must be irrational. QED or whatever it is. Blah, blah, blah. And now let's go solve some new problems.